Currents on the bay can move at 2 to 3 knots or even more. Under the gate, they can reach 4 or 5 knots. In other words, they span the range of speeds at which we paddle. They're also responsible for the bay's most active water. So when we plan a paddle, they're usually a factor. This video will cover how the bay's currents behave and what causes them, and we'll look at techniques for moving against a current. To begin, let's quickly watch a complete 12-hour current cycle. We'll start when the tide outside the gate is just about to rise and push into the bay. We'll step forward in half-hour intervals. The water pushing into the bay initiates a wave of inward motion, which strengthens, then weakens. And now water draining out through the gate initiates gateward motion, which strengthens and weakens until we're back where we started. Before we look closer, let's cover some terminology. At any given location, when the water is moving away from the gate, that's a flood current or flood. When the water is draining back toward the gate, that's an ebb current or ebb. The moments in between, when the water is briefly going nowhere much, are slack water or slack. Slacks can be qualified as a slack before flood or a slack before ebb. The moment in a flood or ebb when the water is moving fastest is max flood or max ebb. Now let's see that cycle again. We start at slack before flood at the gate. The rising tide outside the gate is just beginning to push into the bay. Most of the bay is still ebbing. An hour and a half later, the flood has spread into San Pablo Bay, but the Carquinez hasn't got the message. It's still ebbing. 3 hours in, the gate is at max flood. All of the bay is now flooding. Now the Carquinez has reached max flood, but everywhere else the flood current is slowing. 6 hours in, at the midpoint of the cycle, the gate is just about at slack before ebb. The falling tide has started to let water drain out of the bay. Up north, though, there's still a weak flood. Now it's max ebb at the gate. Just as with the flood, a wave of ebb sweeps northward, so that when we're back to slack before flood at the gate, the Carquinez has just passed max ebb. The main take-home is just that different parts of the bay are doing different things at any given time. If you're planning a paddle, it can be useful to look at the overall pattern as well as at individual tide and current stations. To really see the bay in action, I suggest watching the videos by Rusty Chris Holloman, which are linked in the description. This one in particular shows how the currents vary over the course of a month, stronger at the full and new moons and weaker at the half moon. Let me clarify that only water near the gate actually enters or leaves the bay. Most of the bay just sachets back and forth with the tide cycle, often by a mile or a few miles. As we've seen, the bay's currents are caused mainly by the rise and fall of the ocean tides, which alternately push water into the bay and let it drain back out. The bay also carries the outflow of the Sacramento and San Joaquin rivers. Mostly we can ignore that because normal river flow is accounted for in standard tide and current predictions. As discussed in the video on tide and current predictions, big storms and heavy runoff change that picture. Even though this video is about currents, here's a quick word on tides. Obviously, while currents are moving back and forth, the tide on the bay is also rising and falling. Because the bay is complicated, you can't assume any particular relationship between the tides and currents. In some places on the bay, high tide coincides roughly either with max flood or with slack, but in many places it doesn't. When planning a paddle, you should check the tides and currents separately. Now that we've seen the big picture, let's look at some smaller patterns. First, we see that the current organizes itself into streams of fast water flanked by slower areas, often with a fairly abrupt transition. A look at the NOAA bathymetric data viewer shows that the faster water mostly follows the bay's deeper channels, and that the bay largely is divided into deeper channels and shallower flats. Because we can use very shallow water, we have a lot of ability to seek out helpful currents in deeper water or to hide in the shallows from adverse ones. we also see that the current accelerates at pinch points where the bay gets narrower. The one-sided pinch created by a point also accelerates the current right next to the point. Tide text visualization shows this just for big points and makes it look subtle, but it happens at pretty much every point and it can be intense. And by the way, this speed up here is caused by a pinch from below. There's a shoal here in Raccoon Strait. Anytime a point sticks out into the current, you also get an eddy behind it where the water circles back on itself. To see what we can do with eddies, imagine you just had lunch at West Garrison Beach on Angel Island, and you want to continue around the island before heading back to Horseshoe Bay. But it's ebbing, so what can you do? Here's a more detailed look at the currents. Each bay has an eddy, so by hopping from bay to bay and staying close to shore, you get current in your direction most of the way. Eddy hopping like this is not a complete free ride. You do have to round each point against accelerated current. Doing this is called making an attainment. Once you get to the west side of the island, you can go out into deep water to take advantage of the current. Now you've come back from Angel Island and you're at Point Cavallo. Do you head straight in? You don't, because you know there's a robust eddy in this bay and the short route would go against it. Instead, you stay out in the main current until you're nearly opposite the rocks called the Needles, and then you ride the eddy in. And that's our introduction to the bay's currents. Two topics that are covered in the homework and not here are eddy lines, which let you spot currents on the water, and the ways in which currents generate active water.